I thought it might be valuable to take a moment, step back just a little, and define what a piecewise function is, what it does, where it comes from, how we draw them, and what that represents. But I'm going to step back even one step further first and just draw a function in general. Here's one. It's 2x minus 4. I'll prove it. It's a linear function with a y-intercept of -4. It goes through -4 on the y-axis. That's its b, or its y-intercept. And it has a slope of 2. From that starting point, we went up 2 and over 1. And we continue to go up 2 and over 1 for the rest of eternity, or backwards, down 2 and back 1 if we're going the opposite direction. And that's just a function. A function's job is to take an input and give you an output. A graph's job is to show you all those inputs and outputs at the same time. If I were to take an input of, let's say, something like 3, an x value of 3 spit into this function, substituting 3 in for the x, gives you 2 times 3, which makes 6, minus 4. So a 3 input gives you an output of 2, and I can see that right here on the graph, that an input value of 3 spits out an output of 2. And every point along this red line, even the ones that are in between the intersections on the graph, corresponds to the input that you spit in and the output that it spits back out. So we can do that with any point along the line. We can do that with any function. In fact, there's nothing magic about this function. I could draw another one. It is -1/3 x minus 4. It has a slope of -1/3, so this one goes down instead of up, but it has the same y-intercept of -4. And again, there are inputs and outputs for this function, and all it does is it represents something in the real world, what something costs or how many of something there is. It's a mathematical model to represent that real world thing. I could show both functions at once, but there's a challenge there. If both functions are f functions, if both are the same function, if both are represented at the same time, then at any given time, if I had an input value, there would be 2 output values, and that's not good. If I'm going to have a function, if I give it an input, I want to get a definitive single answer out. Now, there's nothing wrong with defining both of these functions, of course. It's just that I need to limit where one function is good and where the other function is good so that I get one answer no matter what input I put in there. And I do that through what's called a domain restriction. By putting the if x is less than 0 and if x is greater than or equal to 0 on here, I say trust this graph at this moment and trust that graph at other moments. And I can show that here as well. The 2x minus 4, remember, was the red line. And what I'm going to do is I'm going to turn off the whole red line and leave just the part that I'm actually interested in. The 2x minus 4 should only be good if the x values are less than 0. For the x values that are more than 0, the red line is immaterial. It doesn't exist. It's not valid. So we turn it off. And the green line, the -1/3 x minus 4, it's only good for x values that are greater than or equal to 0. By turning off the parts that I'm not interested in. The green one now doesn't exist for x values that are less than 0. It only exists for x values that are more than 0. And that's neat. What it does now is it says if you give me an input value, say 3 or any other, then I can give you one output. And there's no confusion about which output it's supposed to be, which one is the right one for that particular time and situation and input value. So that is a piecewise function. One of the challenges, though, is that this one has its intersect at 0. That doesn't have to be. You can have its domain break at any value you want to have it at. In fact, let me demonstrate that for you and put it anywhere. I can put it here. I can put it here. I could put that domain break at an intersect of 3, for example, which is that same input that I've been using before. Okay, now that changes how this would be written. It no longer would be if x is less than or greater than 0. Now it would be if x is less than or greater than 3. So now I've drawn the newly updated function using the same function rules, only using a domain break this time at an x value of 3 rather than an x value of 0. And I can move that anywhere I want. And it's actually a pretty neat deal, that domain break going anywhere you want it to. Huh? So now the red function is good on the left side, the green function is good on the right side, And all I need is to properly define in my function definition where that domain break is. And I'm left with only one challenge. If I look at any particular input value, I have a single output value with one ambiguous point here at that x value of 3. Which one of those graphs should I trust? Which one is the right one? Well, if you look here in the function definition, you can see, because of the or equal to mark, that if I'm right at 3, the top one, the red one's no good. It's the bottom one, the green one, that I should trust. So if x is 3, use the bottom one. And I have a way to show that here on the graph by putting dots on the graph. Because the green one is the good one, I need a solid dot there that says, trust me. Because the red one is the bad one, at least right at 3, I'm going to put an open dot to say, don't trust me, go look at the other one. So that's the way we communicate visually on the graph which one of these functions, which one of these function rules is the one you should trust. And that is a piecewise function. It can break anywhere you like it to. We have to define which line to use at the break with the line or with the solid dot. And it gives me an output value for any input value, even if my function definition has to change from one part of the graph to another.